Okay, so this video is going to be the first of the 4 Unit 9 big explanation or proof type problems that we'll come across. And then I'll pick one of these 4 and give you essentially a quiz or a test on it. It'll go in your test grade. Okay, so in this one, you've got a surface. The surface is defined by z equals a function of x and y. And this point right here, this point on the surface is P. And you've got tangent lines in the x direction, t sub x, and tangent line in the y direction, d sub y, that fall on these curves of the x and y direction on the surface. And anyway, the question is, why is the tangent plane given by this equation right here? So now I'm going to give you the diagram with the problem if I happen to choose this one. So one of the things we'll need to do is define the letters on there so we can refer to them later on. So down here, I'll define some of these things. Or actually, I'll do it on the side here so we can kind of fit more underneath. So right here, let's let S be the surface. Defined by z equals the function of x and y. So there's one thing. Let's see, we've got P. So let P be the point x naught, y naught, z naught, where z naught equals the value you get when you plug in x naught and y naught into the function. We've got c sub x and c sub y, so let c sub x and c sub y be the curves. It's on S through P in the x and y directions, respectively. Let's see, what else? We got t sub x and t sub y. So let t sub x and t sub y be tangents to c sub x and c sub y at P, respectively. Let's see, and then we need to define what a tangent plane is in this case. So let's see, the tangent plane to S at point P is defined as the plane containing t sub x and t sub y. So let's see. And then ABC, the idea of ABC is that that vector right there is a normal vector to the plane. So let vector ABC be, and really it has to be just any vector normal to the plane. Any vector normal to the tangent plane. This tangent plane, let's say. So then we can say, therefore, ABC dot, and then we choose a general point in this, right, x, y, z. And I'll probably erase that in a minute so it's not in the way. But that means that x minus x naught, y minus y naught, z minus z naught equals 0. That gives us the equation of the tangent plane. So let's multiply that out. So we get a x minus x naught plus b y minus y naught plus c z minus z naught equals 0. And then I'll rearrange it a little bit. So c z minus z naught equals negative a x minus x naught minus b y minus y naught. And then notice the equation that we're given has just z minus z naught by itself, so I'm going to divide both sides down here by c and end up with z minus z naught, these are all therefores, equals negative a over c x minus x naught minus b over c y minus y naught. Okay? So we're up to there now. Well, here's kind of one of the major tricks here. So I want to look at the plane. Let's look at the plane y equals y naught. Okay? Well, y equals y naught is the plane where x can be anything and z can be anything, but y has to be the same y value as right there, which is everything along here in this plane. So you might be able to tell it actually cuts right through that c sub x. You might be able to tell, right? So if we look at this plane here, the y equals y naught plane, let me come back down here. Right? Y equals y naught, and let me rewrite this. Then z minus z naught equals negative a over c, x minus x naught, minus b over c, and then we can use substitution and say instead of y minus y naught, it's y naught minus y naught. Well, this goes to 0, right? So then we're just left with z minus z naught equals negative a over c, x minus x naught. Right? Well, if I sliced right through this plane here, if I sliced through the surface and through the tangent plane and everything, the intersection of that plane with the tangent line is t sub x. Right? Well, I'm left with this equation down here. So this equation is actually the equation for that line, t sub x. Right? So notice here, this line is in point slope form. And has the slope negative a over c, and is the slope of t sub x. Right? So we know that the slope of t sub x can be found, oops, or let's say can be given by the partial derivative f in the direction of x when we plug in x naught and y naught. So negative a over c is the same thing as f sub x when I plug in x naught, y naught. Okay, so here's the substitution that we're going to use. Now similarly, we can do the same thing going this way instead. If we look at the x equals x naught plane instead, then I'm chopping through this surface and I'm cutting right through this part of the surface and right through t sub y on that tangent plane. So if I do the same thing, similarly, if we examine the intersection of our tangent plane with the plane x equals x naught, we find that we can show that the slope negative b over c is the same thing as f sub y when we plug in x naught, y naught. And then putting it all together, therefore, we can rewrite the equation of the tangent plane as z minus z naught equals f sub x at x naught, y naught times x minus x naught plus f sub y at x naught, y naught times y minus y naught. Okay, and there's the end of that big kind of proof. Now, one thing to note, I've run across this in the past, students sometimes forget that that's really just one term right there. That's a single number, and this is a single number. It's the slope, and this one's just the slope in the x direction after you plug in x naught and y naught, and this one's the slope in just the y direction after you plug in x naught, y naught. Okay, and this should kind of feel like point slope form, but with an extra dimension added in. So instead of a straight line, you get a straight plane. Okay. By the way, there is a way to extend this. This is the tangent plane approximation. You learned in 2D calculus how to get that linear approximation right there. Well, the tangent plane is a linear approximation to a surface. You also learned that you can take Taylor polynomials and get like a quadratic that approximates it better, or a cubic that approximates it better, or a quartic that ends up approximating it better. You can keep going and end up with better and better approximations till eventually you're going out several degrees and you end up hugging the curve. And the same sort of thing happens in multiple variables, where you end up with these surfaces that end up hugging the curve, and the way you do it is by adding in these extra terms using later derivatives. So eventually we'll come up with a formula for that just so you can see it. Okay, I hope that helps a little bit, and I'll see you guys soon.